Okay. Since I have a meeting. Okay, important meetings. Okay, so let's we continue for this chapter, which is chapter one. Okay, and introduction of is it introduction the concept of stress. Okay, so this is the introduction. So we discussed previously how to determine the force for each members. Okay, by using method of join. Right. And then we already discussed also tutorials. The main things is if you have a force, okay, if you have the what is it the structure, the first thing that you have to do is to draw a free body diagrams, okay, and then you need to solve it by using the equation of equilibriums, okay, total fx, total fy, as well as total moment, okay. So another one is by using a method of section, okay. I think all of you also already know about this method, okay. uh, this one, so what you have to do is you have to cut for example, if you have a beams, okay, if you want to determine the force at certain parts, so you have to cut that beam, okay. So this methods is used to determine the internal loading in a member. If you look at here, if you cut in the middle of this beam or member, so we can see, okay, we can uh, find here internal tile force, which is opposite direction, okay. So similarly also, if you do this one is if you introduce force in the for the tension direction, okay, this one is for the compressive force, okay. So if a body is in equilibrium, okay, any part of the body is in equilibrium, so you have to remember that generally we will analyze in equilibrium condition, okay. To find the force within members, cut each member into two segments, just like this one, okay, and expose each internal force as externals, okay. So this internals, so you have to you draw the arrow so that we can see the internal force, okay, just opposite direction, okay. So the design of any structure members require the material used is able to resist the loading acting on the member, okay. That means, okay, finding the force acting within the member to make sure the material can resist those loads, because uh, yeah, we have to analyze the force that we introduce to the members, okay, so that we can determine what's the minimum force that you can introduce to the members, so that we can reduce the cost, okay. This internal loading can be determined by the method of section. So the advantage of the method of sections, only we analyze at certain part of our target section, okay. Not this is different with the method of joins. You have to analyze each join just to determine or force for one members, okay, for one beams, okay, something like that. Okay. So what you have to do is, for example, this one, okay, determine the internal force acting on the cross section at C. Okay, what you have to do is determine the support reactions. If you look at here, okay. So support reactions, if you still remember, you have to refer to the previous table. This is the support reactions, okay. And then cut beam at C and draw FBD diagram, okay. Or you can start with drawing with the full body diagrams, okay. This one is going to be roll, okay. This one is fixed, so it's going to have uh, AX as well as AY. This is if full free body diagram, okay. This one is BY, okay. This FBD include the internal force acting at C. So it's stated that you have to cut at the beam at the point C. Okay. So this is why what I told you that this is the overall free body diagrams, and then we gonna cut this one, okay, including the internal force. So you have to remember that once you cut, okay, there's gonna be internal force. There is a normal, okay, as well as this one is more to shear stress. This one is the uh, moment, okay, and then apply equation of equilibrium. So NC is the internal axial loadings, okay. V and M, V is a, I think is a shear, internal shear, okay. M is a moment, okay. So this is the examples, okay. So as I told you, this V is the opposite. If you push into this direction, right, okay. So internal force, either you want to upper direction or bottom directions is up to you, okay, just based on this your sense, okay. So positive internal force is gonna be go up, okay, and then positive for the moment is gonna be clockwise, okay. The loads on the left and right side of the section are equal in the magnitude but opposite in direction. So if you look at here, that opposite in direction but same magnitude. This is because when two sides are reconnected, the net load are zero at the sections. So if you look at here, that if this one is if you cut, okay, so this one is positive, this one is this one is negative, this one is for positive. So when you connect these two, okay, so it's become zero, okay. Okay, so this is what is the meaning of the internal force. Okay. So let's see the how to do the analysis for by using a method of section. Okay. First, determine the support reaction or joint force you need to that you need by drawing FBD of the entire structure. So have I told you? Okay, FBD entire structure, this one, because you want to determine the support reaction. Okay. And then section at the place where you need to determine the internal force. Okay, you have to cut. Okay, any section that you for the target sections. Okay, and then you have to draw free body diagram for the section, and remember to show the internal force NV as well as M. Okay. Keep all distributed loadings, couple moment, and force acting on the member in their exact location. Okay, and then NVM at the section. Okay, and then you apply equation of equilibrium to determine unknown forces. So please remember, you have to cut. You have to start with the uh, uh, zero unknowns, not zero unknowns, the minimum number of unknowns. Okay. Okay, so let's see these examples. Okay, the 5,000 kilogram engine is suspended from a crane boom, okay, as shown below. Okay. Determine the resultant internal loading acting on the cross section of the boom at point E. Okay, so what you have to do is you have to draw full free body diagram. This is a full free body diagram. If you look at here, that this one is the fix. Okay, D also fixed. Okay, and then point B is just a weight. Okay, so if for full free body diagram, you can put arrow here. This one also can put arrow here. Okay, and support reaction. Okay, so just draw. No need to draw here. Okay, since we want to determine the resultant internal force, okay, acting on the cross section at the point E. So you can just draw arrow here. So it's tend to this direction. Okay, if just by your sense is gonna be this direction because we put a weight here. Okay. Okay, so what you have to do is you start with the minimum number of unknowns. Okay, since if you want to determine the internal force and the resultant internal force at point A, okay, the first thing you have to determine is the unknowns. Okay, A as well as Y. This one FCD also is unknown. Okay, So what you have to do is you start with the moment A. Okay, so that we can reduce. So this one AX and Y is going to be 0 at this point. Okay, so we can determine F, C, CD. So moment at A, if you look at here, if you put point here, and this is going to be counterclockwise, right? Okay, so since it's going to be counterclockwise, FCD, okay, times with this one is similar. Is this in term of the ratio? Okay, this one theta. Remember for the trigonometry. Okay, A, B, C. Okay, so this one is if sin theta, okay, is equal to A divided by C, right? So this one 3, 5. Okay, sin theta. Okay, times with 2 meter. Okay, minus with this one 500. Okay, times with 9.0 and 9.81 for the gravity and the distance 3 meter. So we can get FCD. Okay, once you determine FCD, okay, this one is going to be resolve the force to Fy and Fx. Okay, so you know this force already. Okay, so since you know already from the after you calculate by using moment equal to 0. Okay, so you can determine either you want to start with the total Fx or total Fy. So if you can hear that start with the total Fx and then Fy, it doesn't matter. Okay, because it's only one unknown in either to the x direction or y direction. Okay, so once you determine the internal force, okay, once you determine once you determine the reaction force, okay, it's stated that you have to determine the internal edge and internal force at point A. So what you have to do, you have to cut. Okay, so you have to cut this one. Okay, and expose the internal uh, internal force. Okay, you have to cut this point. Okay, so just take this section. Okay, I think either section is possible. Okay, either you want to start with one, also this one. Okay, but we can use this one. I think this one is much better because it's easy. Okay, so we have AX and AY. This one you have to resolve again. Okay, and then you have to resolve again. Okay, so after that, okay, just determine the internals NE. Okay, so into the FX directions. So we know this one. Okay, just total FX equal to 0 since. Okay, and then what else? You can determine the total NE. Okay, this one determines. Okay, another one is VE. Okay, VE is total Fy. Okay, only one unknown, so you can determine, and then we can determine more moments. Okay, either you want to determine to here or here. I think this one is much better. Is moment, since moment is here. Okay, and then we can calculate 2452 times with the direction at point E. Okay, ME is no need to times with the direction because M is already the moment, and the unit is including with the distance. Okay. Okay, any question about this method of sections? It's just, I think it's like recap. What have you learned from the static? Okay, I think you still remember this method. I guess okay. I guess you are still remember of for this method. Okay.
Doctor.
Yeah.
Doctor.
Yeah. Apa dia? What is it?
Do we have to state whether the beam I mean, always state that the beam is in tension or compression.
Okay, and that one is for example this one, right? Okay, I think it's possible. Yes, some we need to what is it to state the tension or compression. Okay, for example, in case of trust. Okay, in case of trust, generally you have to state the member in compression or tension. But here we have never state you have to include the tension or compression. But you can put at the tension or compression. It doesn't mean. Okay, okay, boleh. So for example, this one, right? For example, this one is our target is to determine the internal force. Okay, but in case of thrust, for example, this one. Okay, for example, this one, yes, you have. I think you have to state at the member is in tension or compression. Okay, so for example, if you found that this member DE, okay, in this direction, your arrow, and this one is the direction. So your value you should put at the end of the answer T as a tension, okay, and C as a compression. Okay, you have to put. Okay, so can you do this tutorial just to recap what have you learned from the static loading on the truss as shown. Okay, the force in member BC, BE, and EF. Okay, take a cut through the members BC, BE, and EF. Analyze the top section. Draw the FBD of the top section. Apply equation of equivalence. So what you have to do is you have to determine force for each member. Can you do? I give you about 5 minutes. This one BC, BC, okay, and then BE, and then EF. So if you use method of joins, you have to analyze for each join, right? To determine only force at for member BC, BE as well as EF. But by using of method of section, okay, where is your target section that you are going to cut? Okay, so this is the target. Okay, so you have to cut this one. Can you do this one? I don't have the answer actually. I left in my house. Okay, at home actually. I left at home. Can you do this one? I think I found the answer. I'll give you 5 minutes and then we can discuss. How about this one? Okay, since you cut here, right? Okay, you cut here. Okay, what's the free body diagram? So if you look at here, then this one I just make it small. Okay. So if you look at here, okay. So what we have to do, we have to draw free body diagram. You cut around here, right? Okay. So our target is just these sections. Okay, no need to draw full free body diagram. So we can start for the cut section. Okay. So if you look at here that this is okay the the cut section. Right. And then you okay. Okay. So this one is 5 kilonewton, and this one is the arrow. Okay. And then this one, another one. Okay, this one is 5 kilonewton. Oh, okay, you cut here, right? Okay. So I didn't take this one. Okay, we have to take this one, this section. Since this one is too many unknown. Okay. This one 10 kilonewtons. This one is 5 kilonewtons. Please complete this free body diagram. 5 kilonewtons. Okay. And then what else? This one is F. This one there's an arrow. F CB. Since you cut here, right? You cut here. Okay. FCB. Yes. This one FBE. Okay. This one FE. F. This one is point B. So if you look at here, there's a 3 unknowns. Okay, and the distance for 4 meter. This one also 4 meter. Okay. What else? So our target is to determine BC, BE, and as well as EF. Okay. So you can start since you already draw the free body diagrams. Okay, you can start with which one? Okay. So for me, I will start with the total fx. Why I start with the total fx? Total fx equal to 0. This one, okay, if you resolve it, okay, you can get to this direction. This direction as well as this direction. Okay, so only one unknown to the x direction rather than you start with the total fy. Okay, can you calculate fbe? So if you look at here that 5 kilonewton plus 10 kilonewton minus with negative fbe. Okay, this one is 45 degree. If you look at here, because same same length. Okay, 45 degree. Okay, so FBE cos and minus, okay, 5 plus 10 minus FBE cos 45. So you can get FBE. Okay, so please determine FBE. And then next is we cannot start with the total FY. Okay, I delete already. We cannot start with the total FY this direction because there is a two unknowns over there. Okay, so what you have to do is to determine total moment. Okay, if you determine a total moment at point E, okay, so we can reduce number of unknowns. So this one is going to be become 0. This one is 0. So we can determine this one. Okay, FCB. Okay, so total moment at point E equal to 0. Okay, so negative FCB is clockwise. Okay, so FCB times width of 4 meter. Okay, minus this one, 5 kilonewtons is going to be to the counterclockwise. 5 times width 4 also. Okay, equal to 0. Okay, so you can get FCB. Okay, and then total FY equal to 0. So you can get EF. Okay. Any question about this method? About these tutorials? I think it's easy, right? Any question? Okay, so if no questions, these are some tutorials with the answer. I hope that you can do these tutorials later. Okay, this is just like a revision of the static. Okay, if you remember in chapter 5, in the static for the title is analysis of the structural. Okay, it's just some revision. I hope that you all of you already remember. Okay, so I think it's clear. So this one you can do by yourself, as well as for the tutorials. Let's we move to the axial loading and the normal stress. Okay, so for the normal stress, the resultant of the internal force for the axial loaded member is normal to a section cut perpendicular to the member axis. The force intensity on that section is defined as the normal stress. So this is what we have to do is we use a symbol of sigma. Okay, so the resultant of the internal force for the axial load member in a normal, so that means P divided by A. Okay, so this one is the normal stress. Okay, just this is the area. This one is the force acting on the member or the section. Okay, so what A is area is depending on the type of materials, not type of material, the shape, or the either is it the what is it, the circular shape, or cylinder shape, either it is like this shape. Okay, this one is like a rectangle or square. Okay, so you have to consider the area. Okay, so if we consider this structure, okay, or beams, okay, 30 kilonewton load was acting on at the end of the beam. Okay, the structure consists of a boom and rod joined by pins here. Okay, at the junction and as well as support. This is the support. So you have to remember this one is the fixed support. They have two reaction. Okay, two reaction force. Okay. Perform a static analysis to determine the internal force in each structural members and the reaction force at the support. Okay, this one, and this one. So what you have to do is, if you still remember method of joints, okay, you have to determine all the reaction force as well as the support. So if you look at here, that we start with the total moment at C, okay, and then we can get AX, okay, and that's total Fx, okay, total Fx, we can get Cx, okay, since we already reduced the number of unknowns. So if total moment at point C, this one we can reduce. So this one is also is cross this line. There's no distance. That's why we can determine AX. If total Fy, since we determine AX, we can determine Cx. Okay, so we can determine it. And then total Fy. Okay, so we can determine AY as well as CY. Okay. Okay. So, however, A and CY cannot be determined from the static analysis alone. If you look at here, so what we have to do, we have to do the trigonometry method. Okay. So if we determine by using trigonometry methods, we can determine FBC as well as another other force. I think you still remember also this triangle method or trigonometry method. Okay, just connect all the force from the knowledge of that you have learned from the static. I think is in chapter 1 or chapter 2. Okay, so you can determine. So one you determines that force. Okay, from the static analysis. Okay, FAB and as well as FBC. So at any section through FBC, this one. Okay, so we have to determine the normal force, normal stress. Okay, so P is equal to 50 kilonewtons divided by the area. Since the area is this, look at here, this is the what is it? Like this shape. Okay, circle. Okay, so you have to consider the diameter. Okay, to determine the area, and then you can get the normal stress. Okay. From the material properties for the steel, allowable stress for the steel is 165 megapascal. So this one is it can stand with the 30 kilonewton of the force? Yes, actually, since FBC is below than sigma all. Okay, so look at here, that is lower than 165 megapascal. So the conclusion, member BC adequate to support 30 kilonewton of load. Okay, so this is the important to analyze the normal stress. Okay, or axial loading. Is it? Okay. Generally, we want to determine the minimum force that we can introduce to the 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 beam or the truss. Okay. Okay, as another example here, we got here that design of new structure require selection of the appropriate materials and component dimension to meet performance requirements. Okay. So if you look at here, that the reason is because of the cost, weight, and availability. the choice is made to construct the road from aluminium. So sigma all is equal to 100 megapascal. What is the appropriate choice for the road diameter? Okay, is maybe still is quite expensive, and then it's difficult to find, to get from the supplier. So we change with the aluminium. What is the minimum diameter for the road? Okay, so what you have to do, just a back calculation. Okay, so look at here that since sigma all is equal to 100 megapascal. Okay, so 50 divided by 100 megapascal, we can get area is about 500 times negative 6. Okay, so based on the, what is it, pi d2 divided by 4, so we can get the diameter. So this is the minimum diameter. Okay, just back calculation. The previous one we want to determine the normal stress, but this one we want to determine the minimum diameter, because we want to replace the materials for the road. Okay, so please remember the road, the area of roads. Okay, pi d what is it, pi d2 divided by 4. Okay, so this is for the road. Okay, the area. Okay, any question about this normal stress?
No, doctor.
Okay. Okay. So another one is how we apply the method of section to determine the axial loading as well as the normal stress. Okay. So this is one of the examples. Okay, if you introduce the force, this is how this is a 60 kilonewtons. Okay, we pull this. Maybe we try to pull this rod. Okay, and this one is you push. This is the example, something like you push, or this one you pull with 60 kilonewtons, and this one is 125 kilonewtons. Okay, both side. Okay, so how can we determine from this problem? It said that two solid cylindrical rods AB and BC are welded together at B and loaded as shown. Knowing that D1, okay, this one, D1, okay, D1 is 30 millimeter and D2 is 50 millimeter. Find the average normal stress in the midsection. So here is stated that the midsection AB, road AB, okay, this one, as well as road BC. Okay, so we have to determine the average normal stress. That means the internal force, okay, sigma. Okay, what is it? So what we have to do is we have to cut, okay, just by using method of section. That's why it's important, method of section and method of join, especially method of section. Okay, you're gonna use this one also in chapter 2 as well, chapter 2 as well as chapter 3. Method of section is very important. Okay, even if you want to analyze uh, the torsions, okay, for each sections. Okay, torsion is we apply the knowledge of the moments, okay, for each section. So you have to use the method of section. So you have to master this method. Okay, so for road AB, if you look at here that uh, we apply this one, we introduce 60 kilonewtons, and the internal force is in the opposite direction, okay, but same magnitude. So we can determine PA-AB. So this is a PA-AB. Okay, so we try to pull right. Okay, 60 kilonewton in 10 tension. Look at here in the left and right direction. Okay, so look at here. So we can get 60 kilonewton in tension for PAB, and then you calculate normal stress. Just divided by each area. If you look at here, is diameter is equal to 30 millimeter. So we can get 84.88 megapascal. Okay, so how about for road BC? Okay, so what you have to do, you have to cut until road BC in the mid section. Okay, you rode until that section. I think you to see the overalls of the force acting on the roads. I think you have to do this kind of free body diagram so that you can see. For example, you start from here. Okay, you can see, and then right. Okay, so you can see the overall of the free body diagram. So you can see which section that you cut. Okay, so if you look at here that we cut between B and C. Okay, so if you look at here, this one is the direction for the PBC. It should be opposite direction. Okay, but we also introduced this was 125 and 125. So during the determination of PBC, you have to include this force. Okay, in the this force is equal to 125 kilonewton. Okay, to the x direction, so we can get PBC. Okay, so just calculate the normal stress and you can get the negative 96.77 megapascal. So if you look at here that you get the negative right here, so that means actually PBC is to this direction. Okay, why is to this direction? If you look at here, this is the higher force we introduce rather than this force. If total is about, this one is 250 kilonewton, that's why PBC to the left side, which is a compression. Okay, and it's called negative. Okay, so you have to remember that. Okay, so it's just based on your sense. Okay, even from here you already you can imagine already that the PBC should be this direction. Okay, rather than this direction, but it's okay, any direction you can guess first. Okay, and then you just correct or just make a statement here that it is a compression. Okay, okay, any question about the normal stress? It's easy, right? Normal stress is the internal and uh, internal force. Okay. Similarly, I think this one is I'm not sure is it the same material they use, but some they use different material. Maybe this one is the aluminum and this one is the steel. Okay, so you have to calculate by using method of section also. Okay, method of section is important until the end of this course actually. Okay, until chapter 3, you're gonna use method of section. Okay, is it clear about the axial loading and normal stress? Okay, for this one, we still not consider the deformation or deflection of the materials. Okay, we're gonna cover in the chapter 2. That's why you have to understand this the normal stress. Okay, we're gonna consider the deflection. Once you introduce a force, how much the deflection is gonna how much is gonna change in your materials. Okay, we use symbol of delta. Okay, if no questions, we move to the shear stress. Okay, okay, so almost finished actually. Yeah, one is just example. I think you can read by yourself. So no need for me to explain. Okay, shearing stress. Okay, so if we introduce a force P and P prime are applied transversely to the member AB. Look at here that this direction and the opposite direction, right? Okay, corresponding internal force act in the plane of section C are called shearing force. It's something like you what is it? What is the example? in the opposite, like you tear the paper, right, or something like that. Okay, so there's a opposite direction. You do the opposite direction, right? Okay, the action is in opposite. Okay, that you can tear the paper, right, something like that. Okay, and then the resultant of the internal shear force distribution is defined as the shear of the section. If you look at here, there's an internal force. Okay, the internal force here. Okay, you try here, and then the internal force acting here. Okay, there's internal force. Okay, is equal to the load P. Okay, the corresponding average shear stress is tau average equal to P divided by A. So if you still remember the internal force, the normal stress we use there, sigma. Okay, but for shearing stress we use the tau. Okay, this similarly P also the force acting. This one is the internal force. So you can get the shearing stress. Okay, just a similar question, almost similar. Only the symbol is the different. Okay, but the difference is we acting the force transversely. We apply transversely. We can hear that. Okay. Okay, so for example here, if the wood joint has a wind of 150 millimeter, okay, determine the average shear stress, okay, develop along shear plane AA as well as BB. Okay, if you look at here, this is the AA, okay, and this one is BB. Okay, so since you pull this one, right, if you pull, okay, and you take out this one, you take out, you pull this one, definitely is another force is going to be opposite the direction. Okay, so this one, because the force is acting on the section AA, okay, due to the force here. Okay, so it's tend to this direction. Okay, we pull and this one is try to hold. Okay, this one is try to hold. Of course the force is to this direction, right, is hold here. Okay, this one is acting on the section AA. Okay, okay, so we can get force for FF, this one, and it's a similar because we introduced 6 kilonewtons. Okay, so F is equal to 3 kilonewtons. This one is 3, this one is 3. I think it's similar because of the same size, the same equally divided. Okay, that's why is it 3 kilonewton. Okay, so total effect you can get this one. And then we have to extract or isolate this one, okay, for section AA as well as BB, just for this section, since we already determined this one, right, this one is equal to 3 kilonewton. The opposite side, this one and this one, is going to be similar, the force, okay, for the section BB and as well as AA, acting on the section AA as well as BB. Okay, so if you look at here for the section AA, right, so total FX V minus, okay, so once you introduce force here, okay, so it's going to be opposite the direction, right, this is opposite direction, the shearing, because there is a shearing here. Okay, this one, okay, this one, since you introduce force, this one and this one also, there's a this force, okay, as well as this one. Okay, so you divide it into two, there's a shearing here. Okay, they're trying to if we introduce more load, okay, and it's gonna be divided into two. Okay, okay, so there's gonna be shear there, shear stress. Okay, so you introduce the force to the left side, and the internal force, okay, is going to be opposite direction. Similarly, also for the section B, you introduce force to this direction, okay, and opposite direction for the shearing. For the V is internal, okay, internal force. Okay, so you just calculate VA and VB on the X directions, and you can calculate the shearing stress. Okay, so what is the name of the V? The definition of V, I forgot. V is this one. Oh, V internal shear force. Okay. Yeah, internal shear force. Any questions about this one? So you can get the shearing stress. Any questions about the shearing stress? Oh, is it finished for the shearing stress?